record on the cloud. Okay, so it's a pleasure to have our very own Marco Aymone, who's going to speak on some oscillation theorems in analytic and probabilistic number theory. Please, Marco.
Okay, so thank you everyone for coming. I'm going to talk about some oscillation theorems, and I'm going to start with Landau's oscillation theorem. So let m of x be a number theoretic function in piecewise continuous, just for to simplify the definition. So the simple definition of a sign change occurs at x0 if our number theoretic function is positive, is non-negative up to a certain up to x0, and after x0 it's negative in a small interval around x0, or if something similar happens to this, the opposite happens. And I'm going to recall you the Landau's oscillation theorem, and this theorem says that if m is a bounded Riemann integrable function in any finite interval, and for some x large x0, this function is always non-negative, that is, we don't have sign changes up to a certain point, then this function, the function defined by f of s equals to the integral from 1 to infinity of m of x divided by x to ds. This function has a singularity at the abscissa of convergence. So this is Landau's oscillation theorem. And so the plan of the talk is going to be divided in two independent parts, separated in a situation where you can use Landau's oscillation theorem and a situation where we cannot use. So the first situation, I'm going to discuss the Chebyshev bias mod 4. I'm going to show that if some weighted version of the Chebyshev bias mod 4 holds, then this produces zero-free regions for the associated L function. And this will be accomplished with Landau's oscillation theorem. In the second part of the talk, I'm going to discuss sign changes of the partial sums of a random multiplicative function. And this is a situation where you cannot use Landau's oscillation theorem. Okay. So let chi4 be the real and non-principal Dirichlet character mod 4. And let me define m of x to be the partial sums of the primes p less than or equal to x of chi4 of p. And notice that this is the race mod 4, the number of primes congruent to 1 modulo 4 minus the number of primes p congruent to 3 modulo 4. And the Chebyshev bias has a long discussion about this. We already have a talk here at the seminar about this by Lucille Devan, very nice talk. And the Chebyshev bias is the observation that mx is negative most part of the time. That, in other words, that we have some kind of more primes p congruent to 3 modulo 4 than primes p congruent to 1 modulo 4. But if you look to the partial sums of m of x, Littlewood proved that these partial sums change sign infinitely often. Moreover, m of x plus or minus square root of x divided by 2 log of x times log of x, this function changes sign infinitely often. But the question that I want to pose here is if the weighted race, let's say m sub sigma of x equals the partial sums of chi4 of p divided by p to the sigma, if these partial sums change sign only a finite number of times. So the first result that I want to call remark 1 is the following. If for some sigma is strictly less than 1 and greater or equal to 0, if the partial sums m sub sigma of x changes sign only for a finite number of times, then there is an epsilon such that the associated L function has no zeros in the half plane big real of s bigger than 1 minus epsilon. So in some sense, if the Chebyshev bias holds, if the sum were negative all of the time, then we would have a zero-free region for the associated L function. And some other results holds for something similar holds for other characters if we make the same assumption of no sign change. And so, okay, this appears to be first just let's say nonsense condition, but where can we expect only a finite number of sign changes depending on sigma? And so the remark 2 that has a very simple proof. If you assume the Riemann hypothesis for the associated L function, then for sigma tending to 1/2 from the right, the partial sums become very negative for large x. So m sub sigma of x is less than or equal to minus 1/2 the logarithm of 1 divided by 2 sigma minus 1 plus something that is O of 1 with respect to sigma. So near the sigma 1/2 is where you can expect no sign changes, assuming the Riemann hypothesis. And so this condition, so we might say that this condition of no sign changes is almost of same strength of the Riemann hypothesis for LS chi4. And now I'm going to discuss the proof of remark 1. And the key point is Landau's oscillation theorem. So how do you use this theorem? First, we take the Euler product of the L function and take the logarithm of the Euler product, and we can write as an infinite double sum, and you first take the first infinite sum and sum out the rest up to m equals to 2. And the first sum we can write as the Mellin transform of the associated partial sums. And the second infinite double sum, all the sum of m up to 2, we call this BS. And note that BS converges absolutely for all s with real part bigger than 1/2. So we can decompose the logarithm of LS of LF S of chi in these two parts. Thus, if we isolate the integral, we have that the integral is equals to the log of L of S of chi minus BS divided by S minus sigma. And note that L1 chi is bigger than 0 for chi non-principal. And the region, a half plane union with a ball centered at 1 with radius delta is a simply connected domain. And so the right side of the last equation is analytic in a neighborhood of s equals to 1. So we can use Landau's oscillation theorem in the following direction. The integral, the integrand, the m of sub sigma of x does not change sign infinitely often, right? So it's either positive or negative up to a certain point. And the point 1 is analytic at the point 1. So 1 cannot be the abscissa of convergence of the integral. So this integral must converge for 1 minus epsilon s bigger than y minus epsilon for some epsilon, and hence this produces the zero-free region that we wish to produce. And so this proves the remark 1. In the remark 2, we observe that under the Riemann hypothesis for LS chi, we have that the partial sums is less than x to the 1/2 plus little o of 1. And this can be seen because the Gini-class series sum of primes chi p over p to the s has analytic continuation to real s bigger than 1/2, and it is all of log of t in vertical strips. So we can use Perron's formula and show that actually we have that bound for m of x. And hence, we have this representation for the log of the L function for sigma bigger than 1/2. So now I just take the first sum, the second sum, and then I sum from n up to 3. The last infinite sum converges absolutely for sigma bigger than 1/3. And so if I isolate the first sum is going to be less or equal than minus 1/2 sum of primes of chi p squared divided by p to the sigma. And since chi is real and quadratic, the chi p squared is equal to 1 up to a finite set of primes. And the function L is analytic, so the logarithm is bounded by some constant. So and the last infinite sum also is O of 1 in the interval sigma bigger than 1/2. And so since the series converges, we have that for some x0, large x0, we have this inequality here. And so this completes the proof of the remark 2. So this is the first part of the talk. Anyone has a question up to here? Okay, so I will move to the second part of the talk, which are going to discuss random multiplicative functions. So let me introduce a Rademacher random multiplicative function. So we start off defining at prime, so f of p over the primes p are IID random variables taking plus or minus 1 with probability 1/2 each. And for each power k bigger or equal than 2, f of p of k equals to 0. So it's a multiplicative function supported on the square-free integers. And this model was introduced by Wintner in the 40s to serve as probabilistic heuristic to the Möbius function. And now I'm going to define m of x to be the partial sums from n less or equal to x of f of n. So I will fix this notation during the talk. So Wintner proved that m of x is less than x to the 1/2 plus epsilon, and it is omega of x to the 1/2 minus epsilon almost surely for any epsilon positive. There were further almost sure improvements by Erdos and by Halas, and the records up to date are from Baskin in 2012 and Lautenbaum and Wu in 2013, which they show that the partial sums is less than square root of x times log of x up to 2 plus epsilon. And considering omega bounds, Harper in in this year, if I recall, I think that was in January 1st of this year, proved that almost surely the partial sums are bigger than square root of x times log of x up to the 1/4 plus little 1 for infinitely many integer x. So we have So we have upper bounds and omega bounds at the level of the law of the iterated logarithm for the partial sums. And so what I'm going to discuss now is about sign chains for the partial sums. Almost equivalent to a same question, which is almost equivalent to sign changes, is about recurrency. In probability theory, we say the stochastic process is recurrent if it visits one of the point in its image infinite times. So I can ask here if the partial sum, for example, is equal to 0 infinitely many times. And so notice that the partial sums, each term in the partial sums has 0 expectation. And so our first question that you can put is if 0 expectation is an indication of infinite sign changes. Because then we have, roughly speaking, equal probability of assuming positive values and negative values. So the answer is not, because not when the random variables are dependent. So the simplest case, extreme case, is take x0 equals to plus or minus 1 with probability 1/2, and xn equals to x0 for all n. So this is a very dependent sequence of random variables, right? Is almost deterministic. The randomness is only at x0. So clearly, n of x does not change its sign at any time, but has 0 expectation. So then 0 expectation is not an indication of infinite sign changes when the random variables are dependent. And so what about 0 expectation and independency? So the simple random walk is recurrent in dimension 1 and 2. So what is the simple random walk? Is the probability model for a drunk man walking on the integers, on the square lattice, or on the cube, and that each time it tosses a coin independently of the history, and chooses one coordinate with equal probability. So this is the simple random walk. So there is a famous statement about this. Let me see if I recall. It's something like this: a drunken man always finds his way home, but a drunken bird lost forever. So in dimension 3 and above, the random walk is transient. So what is recurrent? So recurrent is that visits the origin infinite times, and transient is that escapes to infinity almost surely and never come back to the origin point infinitely often. So independence, 0 expectation independence is not an indication of infinite sign changes. So from a probabilistic point of view, it's not clear if our partial sums in the random multiplicative case is recurrent or transient. But in the deterministic case, where the Wintner model is to model the Mertens function, we recall that the Mertens function changes sign infinitely often. And moreover, the number of times for each change in sign in the interval 1x is at least log of x due to the metamorphic properties of one of zeta s. This is a result due to Kaczorowski and Pintz. And the problem here that we have with random multiplicative functions is that our Dirichlet series, f of x, f of s, is almost surely analytic in the half plane, real s bigger than 1/2, but cannot be analytically continued to any bigger domain. So it has all the line real s equals to 1/2 are points of singularity of the function of f or f. So Landau's oscillation theorem and Kaczorek-Spin's method cannot be used here because these oscillation theorems, they need that to have at least a certain regularity of the Dirichlet series at the line of convergence. And the result that I proved together with Winston Heap and Jing Zhao is that almost surely the partial sums plus or minus square root of x divided by log of x times log of x squared change sign infinitely often, almost surely. And just repeating what I have said previously, a random walk on z on integers is recurrent if it visits at least one z infinitely often, almost surely. And just a classical result for Markov chains is that if S of n is a Markov chain, then it's recurrent if at least for one z, one integer z, the probability of Sn equals to z equals as the sum of from n to 1 to up to infinity of the probability of S of n equals to z equals to infinity. Right? Is almost equivalent to a Borel-Cantelli lemma here, but it's not a Borel-Cantelli, it's more stronger than a Borel-Cantelli lemma because the Borel-Cantelli lemma to hold, we need the second part to hold, we need that the sums must be independent. The summands must be independent. So Markov chain is not the points of a Markov chain, they are dependent, but this result, last result here, is more or less related to the Borel-Cantelli lemma. And so a corollary from our result is that for each integer z, the partial sum is equals to z for an infinite number of integer x, almost surely. In other words, the multiplicative random walk is recurrent. And just a simple consequence is that the sum from n up to 1, n from 1 up to infinity is of me squared of n, the probability of the partial sums being equal to z. This infinite sum is equal to infinity for all z integer z. And now I'm going to discuss the proof of this result. And so the key point of the proof of the theorem 1 of infinite sign change is that almost surely as sigma converges to 1/2, the integral from 1 up to infinity of m of x, x divided by x to the 1 plus sigma, this integral converges to 0. And the integral of the absolute value converges to infinity. And so how this captures the sign changes? The proof is by contradiction. So assume that the partial sums change sign only for a finite number of x. So eventually, up to a certain point, is going to be always positive or always negative. So if on the hypothesis that the partial sums change sign only for a finite number of times, these two integrals, they are comparable in size. So their difference must be little, because it must be big O of 1. If on the hypothesis that that we have only a finite number of sign changes. But this is impossible because the one integral converges to 0 and the other converges to infinity. And so the plan of the proof is to prove each of these following limits. So let's begin with the proof that the integral from 1 up to infinity of the partial sums divided by x to the 1 plus sigma converges to 0. So again, we have here the logarithm of the Dirichlet series. We have the Euler product. And we can write the logarithm as an infinite sum of over the primes of f of p divided by p to the s minus 1/2 sum over primes of 1 over p to 2s plus a sum, infinite double sum that starts from m equals to 3. So the last sum from m equals to 3 up to infinity, this last sum is very well behaved in the half plane real s bigger than 1/3. So we can simplify and write the log of f of s as the infinite sum over primes minus the logarithm of zeta of 2s divided by 2 plus big O of 1. Thus, for sigma bigger than 1/2, the log of we are making s equals s only real, making s real equals to sigma, and the log of zeta of 2s is roughly log of 1 divided by 2 sigma minus 1. And so notice that to prove that the integral converges to 0, I am forgetting to say that integral is related to the by partial summation to the Dirichlet series after sigma. So we are going to show that the log of f of sigma converges to minus infinity. So the function must converge to 0. And to do that, we only need to show that the leading term in this last expression is the term in the middle, the log of 1 divided by 2 sigma minus 1. So we need to show that the Dirichlet series, the first infinite sum, is of an order below of the second term. So the first lemma is that almost surely this this infinite sum is less than the second term. I'm back in the previous slides. Observe, keep in memory this second, the term in the middle, and I show him that the Dirichlet series is more or less square root of the term of the middle. This is what I'm showing. And to show the bound above, this bound over a subsequence sigma k going up converging to 1/2 is easy due to the Hoffman inequality, which says that the probability of the if xk is Bernoulli random variables as taking plus or minus 1 with probability 1/2, and ak is a deterministic sequence, then this probability, I can bound above the probability of this infinite series being equal to lambda by the exponential, by something Gaussian. And so I can show over a subsequence this bound, the target bound over a subsequence. But notice that I have a continuous of random variable sigma is varying in a continuous between 1/2 and 1/2 plus epsilon, say. So I have to control stochastic processes in a continuum, not just for a sequence. So the difficult part is to control the maximum size of the Dirichlet series in all the intervals sigma between sigma k and sigma k plus minus 1. Okay, this is the difficult part, but it's not so difficult. I'm going to show heuristics that more or less explain this. So we expect that the size of the Dirichlet series, so here is a bad use of notation, not f is the Dirichlet series of the prime, is not the entire Dirichlet series. This is, I only seeing this now, that is a bad notation for here. So F is the Dirichlet series of the sum over primes, of undependent summands. So f of s minus f of t, I choose a dense enumerable set inside sigma k minus 1. Typically is going to be the set of the g-adic points of this interval. So we expect that the size, the difference of between f of s and f of t, is bounded above by the extremes of the interval. So we want to maximize the variance between them. So it's going to be bounded above by f of sigma k minus f of sigma k minus 1. And this later we expect that it behaves as the second moment. So square root of the second moment. And then I can use the fact that the function f is analytic, so in particular it's differentiable. And then I can use the mean value theorem for differentiable functions and prove roughly this inequality. And the variance of the expectation of of f prime is maximized in one of the extremes of the interval. So this is going to be less or equal than sigma k minus k minus 1 times square root of that infinite series. And that infinite series behaves as 1 divided by 2 sigma k minus 1. So all I need to do is to construct a well-chosen sequence, sigma k, such that the difference of consecutive points is little o of 2 sigma k minus 1, and such that that some of the probabilities converges. So a sequence with these properties that I can take here is exponential of k to the 1 minus delta for some delta. This sequence satisfies these properties. And so this proves the lemma. And then I can complete the proof of the convergence to 0 of the partial sums of m of x, the integral of m of x. And now I'm going to prove that the integral from 1 up to infinity of modulus of m of x divided by x to 1 plus sigma converges to infinity. And so the idea is again to use the logarithm of the Dirichlet series, which is an Euler product, in which I can write as the first infinite sum minus log of zeta of 2 times sigma plus it divided by 2, but plus some error terms. And if t is different from 0 and is fixed, we have that the log of zeta is well behaved as sigma approaches 1/2. So it's going to be O of 1. And so the logarithm of f of sigma is going to be essentially the first infinite sum. So the trick here is to take a t different from 0. Then one can show that easily show that the series in the right side above has variance 1/2 times logarithm of 1 divided by 2 sigma minus 1 plus O of 1. And then with an extra effort, we can show that the central limit theorem holds when sigma converges to 1/2 of the infinite series normalized by the square root of its variance. So I use here the central limit theorem. So the probability of the infinite sum divided by the square root over a sequence approaching 1/2, this being greater or equal to 100, this converges as sigma k converges to 1/2 to the probability of a Gaussian being greater than 100. And since it's a Gaussian, this is bigger than some delta, or where delta is a positive number. So notice the following: the variance converges to infinity. So the sum will not, if the sum, normalized sum, is bigger or equal to 100, is not going to be modified. Is not going to be, the outcome is not going to be modified if I change a finite number of f of p, because when I do finite modifications, this converges to 0 divided by the square root of variance. So this is a tail event, an event that does not depend on a finite number of the random variables that generate this scheme. So then the Kolmogorov 0 or 1 law says that every tail event has probability positive, has probability 1 or probability 0. So since it has probability positive, it cannot be 0. So actually it's probability 1. So we conclude that the lim sup as sigma approaches 1/2 of modulus of f of sigma plus it is equal to infinity almost surely for any fixed t. And since I can write down this inequality here, modulus of f of sigma plus it is less than or equal to the modulus of sigma plus it times the integral. We conclude that this last integral converges to infinity for fixed t different from 0, and sigma approaches 1/2 almost surely. So this proves the convergence to infinity of the integral of the absolute value. And so just a comment, Harper private communication said to me that the methods that of the proof of the large fluctuations for the partial sums of random multiplicative function, the result that he proved that we have omega bound of the size of square root of x times log of x to the 1/4. This method can be modified to produce sign changes. And in the day that I uploaded to archive this joint paper with Winston Heap and Jing Zhao, Oleksiy Klurman told me that in a joint work with Lanzori and Munch, they claim that there are at least log of x and at most square root of x sign changes in the interval 1x. And so I'm going to discuss now random completely multiplicative functions taking plus or minus 1. So observe before that we have random multiplicative functions were supported on the square-free integers. And now I have random completely multiplicative functions that take plus or minus 1. So it's not totally clear if this will have infinite sign changes or not, because now we have a bias towards the square root of x, because when take completely multiplicative, notice that f of p squared is always equals to plus 1. So we have a bias toward in the direction of the perfect squares. And the previous calculations does not work here because we do not have convergence to 0 as sigma converges to 1/2 of the Dirichlet series of f of sigma. So f of sigma here will behave as 1 divided by 1 to the sigma minus 1 up to the 1/2 plus little o of 1. But by a result of Harper of 2013, he proved this very nice result which says that the supremum over T between 1 and that quantity of the infinite sum being less than log of 1 2 to the sigma minus 1 minus log of 1 divided by 2 to the sigma minus 1. This is little o of 1. So what we have here, we have the following situation. On the one hand, we have that the integral of m of x without absolute value is exploding to infinity as 1 divided by 1 divided by 2 sigma minus 1 to the 1/2 plus little o of 1. And by the result of Harper, the integral of the absolute value is over a subsequence bigger than 1 divided by 1 divided by 2 sigma k minus 1 to the power 1 minus little o of 1. So again, here the proof is by contradiction. If I have only finite number of sign changes, then these two integrals should be of the same size, but this will be a contradiction. They do not have the same they do not have the same size. And so one ending open question that I would like to put is that our methods does not work, for instance, when we take a multiplicative random walk in Z2, for instance. If I define at primes f of p equals plus or minus 1 or plus or minus I with probability 1/4 each. So in this case, I will have a multiplicative random walk in Z2, right? So a question that I would like to have an answer is if this is recurrent, if it visits the origin infinitely often. And I don't know how to approach this problem. Anyone that has an idea is very welcome. And so this was the talk. Muito obrigado. Thank you very much.
Thank you, Marco. And we are open for questions.
I could ask a question about a sort of technical point in the proof, if that's okay.
Okay.
So if you go back, I don't know how many slides, you were talking about having to control the difference between f of sigma k and f of sigma k minus 1.
Let me see how I put here again the slides.
Okay, it's probably not necessary to go back. I could just ask the question and we'll see. So my question was going to be, so since you know that almost surely the integral with the absolute values diverges as sigma tends down to 1/2, why can't you just, for the other part, where you're trying to show the integral without the absolute values tends to 0, why can't you just work with a discrete sequence of sigma? Why is it necessary to know it for all sigma?
Because I have to control the size of the Dirichlet series for all sigma, right?
I think you have to do that for one of the parts, but why do you need to do that for both parts?
Sorry, can you repeat?
So you have the integral with the absolute values, which you know is diverging, and you have the integral without the absolute values. So my question is, if you know that the integral with the absolute values is diverging as sigma tends down to 1/2, if you even just have a subsequence of sigma where you know it remains bounded without the absolute values, doesn't that give you your contradiction?
Sorry, now I'm confused. You are asking about the part of the. I'm still trying to open here the thing.
Okay.
Are you talking about this Dirichlet series with independent summands, or about the over primes only?
So the strategy of the proof is that the integral with the absolute values diverges. The sigma tends down to 1/2. The integral without the absolute values around the sum tends to 0 or doesn't diverge. And therefore, the two things can't be equal, so you get sign changes, right?
Right. Okay, so okay.
So my question is, if you know that the integral with the absolute values diverges as sigma tends down to 1/2, isn't it enough for the other integral, the one without the absolute values, just to work with a discrete sequence of sigma, which approaches 1/2? Because
Yes. Let me think. Yes, it can be only a sequence converging to 1/2. But the things that are so nice here that we have convergence of the entire sequence of the entire function to 0.
Yeah,
independent
sure.
of the sequence.
Sure. It just seemed to make it slightly easier, and because you have this technical bit of the proof to control the increments, which you wouldn't then need if you just work with the subsequent.
Okay, so now I discovered how to. I was sharing my screen, so I'm going to share again. So you are seeing my screen, right?
Yes.
So your question was here, right?
Well, yes, and the bit that you just flicked through on the way here, yes.
Okay, yes. It can be only for a sequence. The first integral can be true only for a sequence, and the proof will work.
Yeah.
Do you have, Adam, any idea for the recurrence in Z2 of the multiplicative random walking in Z2?
Yeah, so I was kind of thinking about it for the last few seconds. So the method for the large fluctuations would tell you that you get large fluctuations sort of pointing in any direction in the complex plane. But that's not quite the same question as you're asking, because it's possible that you could have large fluctuations pointing, let's say, in the positive real direction, and large fluctuations pointing in the negative real direction, and you don't have to pass through 0 exactly to get from one to the other. So my answer is no. I don't immediately know how to answer that question.
Okay.
It's a very nice talk anyway. Thank you.
Thank you.
Does anybody else have a question? I mean, the slides are closed, but I think Marco would happily open it again.
Sorry?
I'm saying that maybe people are shy to ask questions because you closed your slides, but I think that's not a problem. I guess if nobody else. If nobody else has a question, we thank Marco again.
Thank you.
Thank you, Marco.
Muito bom, Marco.
Meu inglês estava muito ruim.
Ah, pô, tá bom.
Bom, ué.
Às vezes tava meio parecido com o russo. Meio forte, mas tava bom.
Fazia com isso.
Peraí que eu tô só pedindo umas dicas aqui de... Tá.
É bom parar de gravar já, né?
Ah, é bom mesmo, verdade. Começar a falar mal do presidente daqui a pouco. Peraí.